start from beginning.
Okay. Now it's recording, yes.
Okay, so we are, as I was saying, doing experiments in the underground laboratory of Gran Sasso, and the experiments we are doing are at the interface between quantum physics and gravity, actually trying to find violations on quantum physics, in the sense that we look for possible violations of the Pauli exclusion principle in relation also with quantum foundation, in particular with quantum gravity. And also, since Loyosh is also here, I'm very happy to see him. We look for collapse model and relations with gravity. And the experiment, it's the first experiment, the one which it's investigating spin statistics, violations of Pauli principle. We are actually looking for anomalous atomic transitions, those which would bring electrons as a third electron on the fundamental level, for example, in copper, but we also test other materials. So we look for X-rays, which have a very specific energy, which we calculate in our programs. In this case, it's 7.7 keV with respect to 8 keV. The experiment, yeah, that's the obvious sigla of the experiment logo. And as I was saying, we go in the underground lab of Gran Sasso, which is absolutely stunning. I hope we could organize a workshop or a seminar there sometime in the coming years of the cost action. It's the biggest in the world, in my opinion, also the most beautiful in the world, in this tunnel, 10 kilometers long, connecting two towns, L'Aquila and Teramo. And here, that's part of the group. Group is not very big. It's about 30 persons. And we are mastering technology to measure these very eventually rare events, which are connected with possible violations of spin statistics, which would come and could be related to its other type of violations, so fundamental symmetries, also connected with space-time, with gravity, like non-commutative space-time, existence of additional space dimensions, and of course symmetries like CPT or Lorentz symmetry. And how we are doing this, we are looking for these anomalous transitions. In copper case, it's in the middle of the normal copper transitions, which we still see because we can't get rid of all the background. And we measure the signal by circulating a very high current, 100 of amps, through a copper target, which is considered the signal histogram, while the background one is the one without current. And we already set extremely strong limits to the probability of violation of Pauli principle, less than 10 to minus 40 something for electrons. Quite recently, we related this with quantum gravity models, with various types of quantum gravity models, where the probability of violation is connected to the scale of the space-time non-commutativity emergence. And here I hope that we can find some common language in this cost action. And it's also a function of the energy. So we published this paper 3 years ago, where we put the strongest limit on non-commutative quantum gravity models, going beyond the Planck scale in the version of theta Poincare, approaching Planck scale, which you can't do with accelerators in another version, but you can do with extreme precision experiments. And I hope we can discuss further on what you can learn within our working group context. We also tested other models. We are now actually going towards power 3. So this is how the connection between the model, which is the power of this ratio, and the probability limit we find. Now we are approaching this Kowalski-Glickman small-in model, which we are still far away, but we are coming. And we are also wishful to go towards directionality, so magnetic field inclusion. The other category of experiments we are doing, we look for signals related with the collapse of the wave function, in this case related with gravity, but not necessary as an answer to the measurement problem, which in this case, it's a modification of the Schrödinger equation with nonlinear terms, which are actually naturally, or at least that's the wish, collapsing the wave function, which could be also seen as a decoherence in a kind of gravity quantum field. And here we have a ratio. The spectrum in this case is continuous of the radiation we are going to measure. And it goes like a power of the energy with some parameters which are connected to the model. And again, we have these detectors in the underground lab where we measure this radiation, extreme rare events. We published some years ago this paper where we excluded the simplest version of Penrose and Dioggi model, Dioggi-Penrose DP model, and now we are working. So that was white noise. Now we are going towards more sophisticated models where we include the atomic structure as well as memory and so on and so forth. What I'm expecting in this working group in this cost action is how can we design, how can we use at best our data? So how can we design eventually other type of experiments suggesting quantum effects in gravity at low energy? And how can we connect all this, including spin statistics with metrology? And if any other suggestion would come, would be absolutely fantastic. So my hope is that by the end of the action, we will be able to design experiments, not only thought experiments, but also do them in the lab to test gravitational decoherence, to explore the role of quantum reference frame and covariant measurements theory in these precision experiments, and bridge relativistic quantum information protocols with gravitational metrology. And I'm done, just not to take too much time. So that's a brief introduction of what I bring into this cost action. Thank you very much.
Yeah, thank you very much. Yeah, that was well on time. So yes, is there any questions from the audience about what we just heard? So you gave a talk, the first seminar talk in our seminar, right? So that was
right, with more details on all
a lot
this,
more
right.
details.
Yes.
Yes.
So I'm an experimentalist. Keep that into account. If you have any idea, even if it looks crazy, just come to discuss it.
Yeah, I think this is a very good point. I think we need that's particularly the aim of WG2, right? So to bring
absolutely
and theories together.
Exactly.
Are you going to be at the RQI North?
No, unfortunately, because I'm in another workshop. Unfortunately.
But hopefully there will be another chance.
Absolutely.
Meet in person and discuss.
Absolutely.
So is there anyone? Joshua?
Hi, Catalina. Thanks for the introduction. Beyond the tests of phenomenological modifications to gravity or quantum theory, does your group have any interest in like these sort of theory-independent tests of the quantumness of gravity, like these entanglement-based tests or other kinds?
Yeah, we certainly do have. We only need to understand what is the measurable quantity and check whether we master it in our present technology or we need to develop additional technology or totally different technology. Yes, we do.
Okay. Okay, great.
So
then
we should get in touch.
Yeah, exactly.
Sure.
Please use the chance and then.
Absolutely.
You can find, I think you can find the data, like contact information, email addresses on the cost website, not on the website of our cost action that is not ready yet, but on the website of cost. So there's the list of all participants, and I think there's also contact details, as much as I remember. Definitely of us. So then you can find email addresses of each other and then just contact each other. So the next speaker is now Samira El Gaida. Is that correct, how I pronounce it? Samira? Maybe. I don't know. Maybe she's not present. No, not present. All right. Okay, then just the next one. Paolo.
Yes. Hi.
Okay.
Good afternoon to everyone.
Yep. Hello.
Okay, I'm gonna
Nice
share.
that you're here.
Sorry?
Great that you're here.
Yeah, I'm happy to be here to share what I'm about to share. So okay, can I start?
Yes.
Okay. So thank you everyone for coming today listening to me too. My name is Paolo Fragolino. Today I'm going to talk about quantum reference frames, relational quantum gravity. I don't know. Wait. Okay, do you see it now? Okay.
Yeah.
Okay, so my scientific background, I got my master's degree in theoretical physics at the University of Bologna, and I've taken many different courses, such as like quantum field theory, standard model, general relativity. But most of all, I've been really interested in during my master in a course about quantum cosmology and canonical gravity. And for my master thesis, I worked on the decovariance effect in the QGEM experiment. There is an experiment that aims to prove the quantum nature of gravity via entanglement. And I've done it at the University of Groningen with Professor Anupam Mazumdar. And it also resulted into a paper that you can find on here. So I've been interested since my master in both quantum foundations and quantum information theory, and also like strongly interested in general relativity, canonical gravity. And right now I'm doing my PhD in quantum gravity at the University of Alberta, under the supervision of Saeed Rastgoo, that is going to talk later and on page. And I started like a few months ago. So I've been interested basically in two topics for the moment. The first one is the problem of time in canonical gravity, because we know that in general relativity we have diffeomorphism invariant that leads to the fact that the total Hamiltonian is a constraint. So we have a Wheeler-DeWitt equation of this type, that the action of the Hamiltonian on physical state gives zero. And this, of course, leads to a frozen time formalism, no? Because the Hamiltonian generates time translation. So the problem is, how do we recover time evolution in quantum gravity? The other topic that I've been really interested to is quantum reference frames. It starts from quantum foundation and quantum information theory. And basically, it takes into account the fact that reference frames are always physical systems, such as like rods and clocks that interact with observed systems. But ultimately, any system is quantum, so it is fundamental to allow reference frames to have quantum properties too. And one of the most beautiful results, in my opinion, of quantum reference frame is the fact that entanglement and superposition depend on the observer. And this, when I first read about that, I was like, it was very nice discovery. So it turns out that there is actually a connection between these two topics, so quantum reference frame and the problem of time in quantum gravity. These are two papers for reference that you can find on the archive. And what I've learned is that in general, gauge symmetries in quantum gravity call for a relational description of reality. So this means that physics only makes sense when a dynamical variable is described in terms of another dynamical variable. So we have to start to talk about dynamical reference frames, so reference frame associated to physical system. And of course, after quantization, this dynamical reference frame have quantum properties too. So we're kind of forced to use quantum reference frames. So this is basically the idea between this connection. And in particular, the fact that about the problem of time, the Wheeler-DeWitt equation just expresses the fact of that our theory is independent of, our physical states are independent of from redundant gauge degrees of freedom, which in general relativity are coordinates, for example. So it just tells that we have a redundancy in our description. So and the Wheeler-DeWitt equation in particular can be interpreted as the equation that contains all the existing points of view at once. So all the reference frame, all the quantum reference frame later at once. That's why it's usually called in this literature a perspective neutral space, the Hilbert space associated to. And this is a general scheme of the quantization procedure. So we have the physical Hilbert space on top with physical states that contains all the points of view at the same time. And you can build a map. For example, if you have three particles, A, B, and C, you can describe everything from the point of view of C by first a trivialization, that is just a unitary transformation that makes the C degrees of freedom explicit. And then you project over a state C, for example, as you can see here, Q equals to 0, to obtain an Hilbert space of just particles A and B from the point of view of C. And now this is an Hilbert space that makes more sense physically because you can interpret everything from the point of view C. So probability, observables, time evolution, you are able to recover time evolution too. And in general, this is the procedure. Of course, you can do the same thing with any other particle. So with particle A, and so you obtain particle B and C from the point of view of A. And then you ask, what is the connection between these two different Hilbert space, one from the point of view of C and the other from the point of view of A? And of course, this is equivalent to, like this connection horizontally is equivalent to go up there to the physical Hilbert space and then go down. And it turns out that this transformation has found to be exactly the same as the transformation that was found in quantum reference frames in the literature. So it has all the interesting properties such as entanglement and superposition that are frame dependent. You can also apply this framework to cosmology. The most simple model is FRLW universe, where you have the expansion parameter here of the universe together with a massless scalar field. This is the resulting Hamiltonian. This is a constraint. And this is, of course, the resulting Wheeler-DeWitt equation of this wave that, of course, doesn't make physical sense yet. It means that contains all the points of view at once. In fact, you can use both like phi as a clock for alpha or alpha as a clock for phi. This is in general a physical state that solves this Wheeler-DeWitt equation, and this is the trivialization operator. Sorry, I'm going to go faster. You can also apply this to black holes. That's what I have trying to do, in particular to the interior of black hole for Hastings-Barbero variables. In terms of BNC, I performed like change of variables with alpha and beta, and this change of variables, you obtain this very easy constraint that is much easier to solve in the quantum theory, and it also shows the relational nature of the interior of the black hole, where alpha and beta you can describe one in terms of each other. You can also build quantum clocks with this framework and Dirac observables. In this way, I also leave you a paper for reference. And in particular, I have considered an observable to be the area of the interior of the black hole, and I was able to obtain the evolution of the area in terms of tau. There is this quantum clock, and this is the evolution here, as you can see. So you reach the area equals to 0. That is equal to the singularity when tau goes to infinity. You need an infinite amount of time to reach the singularity, but this is still work in progress. I don't know yet if that phase of the singularity. And anyway, what I expect from this from RQI, I of course I'm really interested to develop an interface between quantum information and quantum gravity, and hopefully this will help also solve problems like singularities in general relativity and other problems like the black hole information paradox. And also, it will. I think that this interface will also help develop tabletop experiments for quantum gravity, or in general, any kind of experiments, quantum foundation and quantum gravity. And of course, the other thing that I hope for is to find new collaborations with someone. Okay, thank you. Sorry if I went like a few minutes.
Yeah, okay, thank you very much.
Sorry.
So we have only time for one short question. Is there someone with a question?
Just a short question.
Yeah.
Yeah, please go on.
This Trinity paper, it really has 3 zeros, 333, and it is named Trinity. How did you manage to make it on archive? The name Trinity and all of those 3 zeros and all of those things to be inside the archive?
I don't know. I found like I just copied the number on archive from the paper. I don't know if it is the correct way. I don't know.
It is. It's very nice.
Okay.
Yeah, maybe a great coincidence. Yeah. I didn't.
Okay. I didn't understand. Okay, now I understand.
All right. Okay, so the next speaker would be Martin Plávala.
Yes. Hi.
Hi. Do I pronounce that correctly? Plávala?
Plávala, yes.
Okay, perfect. Okay, so then yeah, you can start.
Yes, one sec. Just sharing my slides. Sorry, can you see me and hear me now?
Yeah, I see you twice, but I definitely hear you.
Okay, sorry, my Zoom somehow crashed for no good reason.
It's all fine. So, yet now that's working. I see your presentation. I hear you, so you can start.
Okay, thank you very much. So I would like to say that I'm coming to this meeting more from the side of quantum information or quantum foundations. So I know not as much about gravity as some of the other people, but I would like to say that my first paper ever that I did as a master's student was actually on cosmology, so I'm not so hopeless. But what I've been doing for a very long time is that I was investigating these GPTs or general probabilistic theories, not to be confused with ChatGPT. And the main idea here is that this is something like an operational framework that includes classical and quantum theory, but also other theories, such as, for example, PR boxes. And we've been using this for quite some time in quantum information to investigate properties of systems, determine whether something is classical or non-classical, and solve problems of these types. And the framework is essentially super simple because it's just built on the basic idea that whatever experiment you're performing, you start by performing a preparation, as in here on this picture in blue. Then after that, there's some transformations. So the transformations, this can be your system evolving in time, or you make it interact with other systems, you shoot it with lasers or some other things. And in the end, you perform a measurement, and this measurement is just a map that extracts classical information from your system. So it's super simple ideas, but there's a lot of depth in these ideas, and one can use this to derive quite a few results. And if you want to know more, there's a review that you can find that I wrote, which almost completely covers this. Now, of course, now you have the obvious question: can you actually do quantum gravity with this, or does this connect in any sensible way to quantum gravity? And I would argue that yes, although it's a little bit lengthy process. So instead of trying to explain how this exactly connects, I'll just showcase 3 examples where we use these GPTs and results inspired by GPTs to say something about gravity or gravity-related phenomena. And the first one is a collaboration with Marta Marquese that I also saw attending this meeting. And it's a simple question about the proposed experiment on gravity-mediated entanglement. Because when you think back to all of those papers predicting gravity-mediated entanglement, how they computed the experimental predictions is that they take the 2 interferometers and they somehow use the Schrödinger equation to let them interact. And from this, you get the relative phases that give you the non-trivial entanglement. So using these GPTs, we had a simple question. What if you keep the preparations to be as they are proposed in the experiment, you keep the measurements as they are proposed in the experiment, but you change the transformation and you change it in such a way that instead of the systems obeying the Schrödinger's equation, you just replace this with the Newton's laws of motion. So these are the classical Newton's laws that, like, you all know, that just do this, objects fall and things like that. And what it turns out that once you do this, after doing some kind of reasonable approximations, you get almost the same result for the purity of the marginal. So you get almost the same rate of entanglement, and the difference, as you can see here, is very, very small at the time when they wanted to measure. And you can actually already draw some kind of conclusions from this by saying that, well, one can also say that if you have a theory of quantum gravity, whatever it is, it must have some kind of classical limit that leads to Newton's laws of motion. And already this classical limit is sufficient to predict the result of this experiment. Of course, by using the respective potentials, which are non-local, but you can also argue that this is field theory in a Coulomb gauge. So it's, I would say, not so bad, but obviously not what people would exactly expect. As a second iteration of this idea is then that, okay, if this experiment does not really tell us, or in some sense one can say that this experiment does not really certify the validity of Schrödinger equation in quantum gravity, and then the question is, what would certify that? And that's the second result, where we use GPTs to address this question. And what we show in this another paper that's a preprint on arXiv is that you can actually design experiments that would directly measure the generators of time evolution. So you can design an experiment that will tell you whether quantum gravity acts via Schrödinger equation or via Newton's laws of motion or via whatever other linear super operators acting on your density matrix and giving you the time evolution. And moreover, you can actually do this with current atom interferometers. So once you run the numbers, once you assume that you have something like a single cesium atom that you split to follow two different paths, you just need to split it so that the paths are 10 centimeters apart, which is not easy but not impossible, and bigger splits were done. You need to position some external masses M1 and M2 around these paths. You need to have two masses, otherwise you don't really get exactly the results that you want. And you can do this in such a way that you actually eliminate the classical term or the classical limit coming from the Newton's laws of motion. And you observe the purely non-classical effect of gravity of these external masses on your interferometer or on your atom in superposition. As I said, if you want to know more, then the paper is already in archive, so you can look it up. It's very short, and we try to make it as easy to read as possible and not very convoluted. And the one thing that I said here is that we only assume that your generators are linear, right? You know, like so this somehow does not really work well, or does not really take into account that you could have nonlinear modifications of quantum theory. And the third result that's still in preparation with Ruben Campos Delgado, a PhD student here in Hanover, is that how do we say something about the nonlinear modifications? And here we show that you can use something coming from the foundations of quantum theory, and namely contextuality, to propose experiments that would actually rule out nonlinear modifications of quantum theory. And as I said, the paper is still in preparation, but this should be on the archive hopefully this month. And yeah, with that, I'd like to thank you for your attention. And if you are interested about using GPTs or about GPTs in general, then please feel free to reach out.
Yeah, thank you very much. So are there questions about what Martin just told us? Or in general, any direct interest in collaboration now? Of course, they can always contact him later.
Can I ask a question? Short one.
Of course,
please.
Yeah, Lajos Leoshi. Hi, Martin. I came across with your paper, which pointed out that entanglement can be obtained, and that's my question. Do you mean that? So the claim of your paper is that entanglement can be obtained if you replace if you use Schrödinger equation with the Newtonian pair potential. In this case, I don't really see the point, but your point must be different. This time you said that what if we replace Schrödinger equation by Newton, by the simple Newtonian law of force against acceleration, or the vice versa?
Yes.
So what do you mean by that? If I replace the Schrödinger equation, what quantumness is still remaining there? So if
yes, it's exactly replacing Schrödinger's equation with Newton's laws of motion coming from the forces. And one does this in phase space by replacing Moyal bracket with Poisson bracket. And somehow the point was that the quantumness that remains there are the initial superpositions of the two atoms. So in the usual experiment, you have these two interferometers, but they're initially in superpositions. And we somehow try to claim that in some sense, these initial superpositions are already doing a lot of the quantum work.
So the equation is about a phase space distribution, not for the wave function, but for the quasi distribution of what?
In this paper with the Newton's laws of motion, yes, it's all done in phase space using Wigner's functions, but that's equivalent to density matrix.
Yes.
Up to some mathematical problems with not L1 integrability, but which do not pose any problems in this case. But if you actually look at the second paper, the one about measuring the generators of time evolution, there we actually show that you can also do the same with density matrices. And you can basically take the Poisson bracket and apply it to density matrix by running the Weyl quantization in reverse and all of these things.
I see.
So in principle, you can also do everything for just density matrices, never going to phase space.
I see. So, but so the trick is that you drop the wave function, you introduce a phase space distribution, and then you make some classical physics using the Newtonian force.
Yes.
And in the second paper, you point out that this can be done directly on the density matrix formalism as well.
Yes, in position representation.
More or less, yeah. Okay, thank you.
You're welcome.
Okay, perfect. Thanks again for the talk and the discussion. And so the next speaker is Saeed Rastgoo. Did I pronounce that correctly?
Yes, thanks, Dennis. Yes.
All right, perfect. So can you share slides?
Yeah, I'm gonna share screen. Okay, hopefully you can see it now.
Not yet. I just see your name and I know. Now it's there.
Okay, thank you. Great.
Okay, you can start.
Thank you very much. It's great to be here. My name is Saeed Rastgoo. I'm an assistant professor at the University of Alberta, working on topics in quantum gravity. As you see here, several topics. These are the names of the people who are involved or are involved in the topics I'm going to talk about, which are 3 topics. And Paolo already talked about a bit about the problem of time. So let me just give you my at the moment, with my current state of knowledge, my philosophy of how I do my projects. It's well maybe that the universe is a giant mathematical structure. I mean, the quantum fields are complex fields, so basically they're not real in the sense of our level of coarse-grained level, basically. So the foundational principles of the universe might as well be just probability optimization and coarse graining, just somehow combining this stuff when we get the universe out of it. And as you can see, these are highly related to computation, information, and basically, many of the concepts that are in these fields. So I'm a theorist, so I mostly talk about theory. The quantum black holes, as you know, one of my projects is that these are rich labs for new physics, especially related to quantum information. But in order to extract precise and concrete information about them, you have to construct a precise model, and the model usually depends on how you construct it. And what I mean by that, at least in canonical quantum gravity, is that usually people in canonical quantum gravity first at the classical level symmetry reduce the model, so you have a full gravitational model, and then reduce it to spherical symmetric models in classical level, and then you discretize or quantize it. One can argue that actually this is not the general way that the universe works. Again, none of us at the moment know how the universe works in this way, but because we don't have experiments that much. But the general idea might be that maybe you have to find the discretized general theory and then symmetrize it instead of vice versa. And that's what we are doing now with one of my PhD students and one of my collaborators. So the idea is that you take your gravitational theory and in your space-time, you build a discretized, this is like a Death Star here, a discretized model, like a sphere, and you write your Hamiltonian and basically your degrees of freedom on this. So for example, if you're doing loop quantum gravity, you write your holonomies on these loops on this basically graph. But remember, this is not where you're not symmetry reducing stuff here, just building this. And then, so this has a symmetry group, for example, SO3 for rotational symmetry. Now you kind of writing your model on this discrete system, you have already discretized. You haven't symmetry reduced. You have a discrete phase space, and then you basically lift your symmetry group to this phase space and find the small portion of that phase space that is invariant under that symmetry. Now you are symmetry reducing. So first discretization and then symmetry reduction. And then in this space, you will find the Hamiltonian and the symplectic structure, basically restricted to that. And then you do your computations, you find the components of the metric, blah, blah. And then you build your black hole. So we already have done the basic things. So this can be done for any type of symmetry reduced model, quantum cosmology, quantum black holes. We already have done this for the model of loop quantum cosmology, which is different from all the recent models, basically. And this comes out later in summer. And also for quantum black holes, probably end of the summer. The idea is that you can do this and then look at the information theoretic concept in this new model of black hole. More related, maybe even more relevant to quantum information is space-time structure. And the idea common in gravity is that the space-time is not fundamentally, and it might be emergent actually. And usually emergent models have two ways of emerging a space-time. One is condensed matter style, which basically you have fundamental atoms of the space if you want, and then you normalize, you coarse grain, and you get your something that you hope to look like a space-time. Other one is it from bit, very famous one. And this is basically based on Hilbert spaces and correlations and a space from Hilbert space. So we have suggested a model that's the combination. And that combination basically is you take the basic building block of a space as a random graph, basically vertices are the stuff that make space-time, and edges are interaction between this stuff. And then this can be related to a Hilbert space by correlation. For example, correlation functions of the Hilbert space could be related to the distances with respect to the metric, basically the minimum number of edges between two vertices. And if you coarse grain these graph based on the fact that each click on a certain graph becomes a vertex without the structure in the next level of graph, you actually have a description of how entanglement works, because those higher level points, they have actually internal structure in the lower levels, and they can be connected with respect to the metric of the lower level graph. And then you can say that how these spaces, coarse grained spaces, are similar or different using Gromov-Hausdorff distance. And then you can supplement this by continuum limit to get something smooth. Of course, these are all work in progress from here at least. And this is a very combinatorial and rich model based on quantum information. Quantum can be, related to quantum information and quantum computation. And finally, I have just maybe 30 seconds. I'm just going to talk about the problem of time, also part of a space-time problem. And we are using page footers formalism. Basically, it's asking what is the probability of some operator taken as a time. What would be the value of the other operator taking as other part of the universe. And so because of the time, I'm not going to go into too much of a detail for this, but I'm just leaving this here if there are any questions. Thank you.
Yeah, thank you very much for the nice introduction to your work. So is there any question from the audience? Cisco, please.
Yeah, I was curious about this discretization approach. Could you very briefly either compare or contrast it with like the causal dynamical triangulation or quantum graph approaches?
So,
did both?
Exactly.
I'm guessing it's more like quantum graphity.
Yeah, not completely. So this is basically you put a quantum graphity is a little different. These graphs are basically gauge invariant, and then you can actually the model really shouldn't depend on the form of this graph. So in some way they all have graphs like loop quantum gravity, and others. But the distinction is that what you would do is that in quantum gravity, for example, you first reduce and then, well, that's not really, starting from a continuum theory. They have some sort of graph and then define interaction between the vertices, right? We have gravity here, so.
Okay.
Yeah. They don't consider gravity really.
Very quick question. In what sense are the graphs gauge invariant?
So you see that
I mean, it's a continuous. Sorry, could you just elaborate very quickly on that?
Sure, of course. When you write the variables, for example, the holonomy is here, right? Holonomy is in flux and stuff on these loops. They should be invariant under gauge group of the system. So in terms of if you act by rotation on this graph, right? If you rotate this graph, this is invariant in the rotation and locally also on the rotation. So in that sense, this graph is gauge invariant. And the direction of the group, symmetry group of the model. Yeah. Sorry, there's not enough time to explain details. Yeah.
Yeah, I know. I don't want to. Thank you.
So I think there will be more chances. I mean, there will be more talks, extended talks in that seminar in the future. And of course, you can also just meet up if you have more questions and then discuss. So now I would just give a short presentation about my stuff. And then it's already, so I'm already the last. Just by chance, I ended up to be the one in alphabetical order to be the last. And so that's it. Okay, I also give myself 6 minutes, but let's see. I think I'm quicker. All right, so my name is Dennis Rätzel. I'm a researcher at the SARM, University of Bremen. And so my background is actually, so I did my PhD in the Albert Einstein Institute in Golm in Germany about generalized spacetime structures. So it was all classical generalized spacetime structures and quantum field theory in the background independent formulation that was invented by Robert Oeckel, who I saw before here in that meeting as well. And then I moved on from that to what's more towards experiments. I wanted to contribute to the development of new experiments at the interface of quantum physics with gravity and relativity, because I think that's how one can gain by trying to propose new experiments, we gain insight, and on the other side, of course, we need some experimental evidence to test our models. So I think that's a very a strong need for that. And that's two reasons why I like that field, that overlap, that interface. And that's also, of course, the focus of that working group. So my research is split into these 4 subcategories: quantum systems and gravitational fields, quantum properties of gravity, sensing of relativistic gravitational effects, and quantum optics with free electrons, which is completely off. So let's take that off the list. And the rest I would describe as gravitational quantum physics and metrology. So it's really the topic of that group. So I'm a theorist, so I can do a lot of different things at the same time. Right. So just as a short overview of what these categories comprise from my perspective. That's work that I did. Of course, they are much wider than that. So I worked on Bose-Einstein condensates in gravitational fields in curved spacetime, and I worked on entangled photons in quantum memories in gravitational fields and quantum effects that appear in that context, for example. Then in the field of sensing of relativistic gravitational effects, I did some work on the effects of the cosmological expansions on optical cavities and laser ranging satellites. That is in some sense classical, but of course one can ask about quantum metrological bounds here for detecting these kind of effects. But just as a spoiler, the effect is too small, way too small. But the perspectives of measuring the gravitational field of light and ultra-relativistic matter, that's also challenging, but that's much closer. And we're working a lot on that at the moment, also to test modified gravity theories. But yeah, we are working with the Large Hadron, people from the Large Hadron Collider on that to hopefully at some point there will be an experiment measuring the gravitational field of the proton bunches at the Large Hadron Collider. And then in the last category, there's quantum properties of called quantum properties of gravity. I worked on the entanglement in gravitational photon scattering, and again, that's more fundamental. That's completely off from every so that cannot be tested in an experiment. I'm pretty sure. But here the other topic is empirical evidence for quantized gravity from quantum optomechanics. So that's these gravitational entanglement experiments that we heard about before. And yeah, okay, there's of course a dispute on what you can actually tell with measuring entanglement in these experiments, but we worked on a specific implementation with optomechanical systems that you see here on the right, where you have two mechanical systems of two optomechanical systems gravitationally interacting. Okay, so but as I said, for me, there's a need for new experiments that probe this gravity quantum interface, and that's what I'm working for, and that's also what I'm hoping for to get here with the working group and the cost action. So what we want to do and what I want to do is to establish a network of researchers to develop new proposals and roadmaps for new experiments. Together, this could be completely new ideas, of course, and also white papers and strategies, as I said before, to really motivate the community and science administrators to dedicate researchers for these experiments, and also politicians maybe in the end. And then we want also, I think it's important to generate a comprehensive base of expertise and knowledge on the field, and that's also why we are exchanging here and trying to figure out who is doing what, because then we know who we can address if there are problems, and then problems are solved quicker and there's more collaboration, which I think is important. And here, in the end, there is I want to encourage a new generation of researchers through training and dissemination. So like PhD students and postdocs and even master students. There will be schools about these topics. And now, yeah, thank you very much. And I'm looking forward to the next 3.5 years and to work with you as part of the cost action and WG2, and I hope for more of these meetings, and I hope to meet as many as possible of you at the RQI North in Naples this summer.